10.5 notes, polar form of complex numbers, page 4. So we're going to continue what we were doing on page 3. Page 3, we multiply two complex numbers. Now we are going to divide. And so we've got the quotient of two complex numbers. Keep in mind, and let's just write it up here, the quotient, ooh, I hope I left myself enough room, is going to look like this. We are going to divide those moduli, and we are going to subtract the arguments. So cosine theta 1 minus theta 2 plus I sine theta 1 minus theta 2. All right, so here we go. z1 sub 1 divided by z sub 2 is going to be our r sub 1, which is 24, divided by our r sub 2, which is 8, times the cosine of 300 minus 75 plus I times the sine of 300 minus 75. So here's the thing. I could come up with the cosine and sine of 300 and rewrite this in polar form. I can't find the cosine and sine of 75 without using either a sum or difference formula, which feels like a whole lot of work at this point. So I have 3 times the cosine of 225 minus I sine of 225. 225 is the same as 5 pi over 4. That's in quadrant 3, so I know both of these are negative. So I've got 3 times negative square root of 2 over 2. Oops, this should be plus. I don't know what's going on there. Plus I times negative square root of 2 over 2. I was just a step ahead. Which gives me negative 3 square roots of 2 over 2 minus 3 square roots of 2 over 2i. And that's it. B, same thing, z sub 1 divided by z sub 2. I've got 12 divided by 3. Cosine of 40 minus 10 plus I sine 40 minus 10. 4 times the cosine of 30, and I can multiply this through 4i times the sine of 30. Cosine of 30 is square root of 3 over 2, so I've got 4 square roots of 3 over 2, plus 4i, the sine of 30 is 1/2, which gives me 2 square roots of 3, plus 2i. A whole lot easier than finding the complex conjugate, multiplying numerator and denominator. And so there are times when this is going to make life a whole lot easier for us. So let's take a look at what we have next. De Moivre's theorem for finding powers of a complex number. And this is just an extension of what we did to multiply. So if I'm raising something to the nth power, I'm going to take that moduli, raise it to modulus, raise it to the nth power, and then each of those arguments are going to be multiplied by n. They're going to happen n times. So for A, it's got to be written in polar form first. So let's see what we got here. I got r equals 1 squared plus square root of 3 squared, 1 plus 3, which is the square root of 4. So my r is 2. Theta is the inverse tangent of square root of 3 over 1, so square root of 3. That happens at pi over 3. And if we take a look at what we have, 1 plus square root of 3i, if I were graphing that, it'd be positive 1 square root of 3. So I'm in quadrant 1, so that pi over 3 angle is going to work just fine. And so my z is 2 times the cosine of pi over 3 plus I sine the pi over 3. We want z to the 12th. So we've got 2 to the 12th times the cosine of 12 times pi over 3 plus I sine 12 times pi over 3. 2 to the 12th is 4,096. Cosine 12 pi over 3 is 4 pi. Plus I sine 4 pi. Coterminal with 2 pi, coterminal with 0. So we've got 4,096 times 1 plus I times 0. 4,096. Same thing on B. I've got -1 minus I. So let's think about that really quick. -1 minus I is right here. I know what that angle is. That's 5 pi over 4. R equals the square root of -1 squared plus -1 squared. 1 plus 1, we've got the square root of 2. So z is the square root of 2 times the cosine of 5 pi over 4 plus I times the sine of 5 pi over 4. I want z to the 4th, so that's square root of 2 to the 4th times the cosine of 4 times 5 pi over 4 plus I sine. We can see sometimes this is nice the way things fall out. Square root of 2 squared is 2. Square that, we get 4 here. Cosine of 5 pi plus I sine of 5 pi. So that's the same as the cosine of pi. 5 pi is coterminal with pi. I get 4 times -1 plus 4 times I times 0, and we get -4.